BytePair encoding. Packages, we need to verify same torch and tick token that will be used by BytePair. GPT-2 uses BytePair encoding as its tokenizer. It allows the model to break down words that are not in its predefined vocabulary into smaller words. This is how they handle it. Subwords or even individual characters if required, enabling it to handle out of vocabulary words also. The original BPE tokenizer can be found here. This is the original tokenizer. And this is the proper class if you want to go through the code. This is not big program, 117 lines only, and how it is dividing that, converting that into tokens. So the same program what we discussed, encode decode, same is used here. It is taking care of the character set also and handling the tokens which are not there in its vocabulary. Very simple tokenizer used by GPT-2 model. In this lab, we are going to use BPE Tokenizer from open source tick token library. This is where it is available on tick token. This is tick token where we have this library. So it is a fast BPE tokenizer for use with OpenAI models. And this is example here. We'll be using this encoding and you see performance of this tick token. So we are going to use this import lib and then tick token. Check the tick token version we have. It is 0.5.1. Define the tokenizer tick token.get encoding GPT-2. Now this is my word. Hello, you have completed this text, right? Professional certification course. This was my original text. Link, unlink, known, unknown, end of text. All those tokens, I just pasted exactly the same content here. And these are the tokens identifier or the token numbers in this BytePair. Now printing it back, the same, you can see I printed that. BPE tokenizer break down unknown words into subwords and individual characters like this. AKWIRWER. If this word is not there, then this is a simple text with unknown words. This may bring it, split it into individual token like AK, token ID, WIR, W, and then space, and IER. It may bring down like this, split it like this. So we data sampling with sliding window. We train LLMs to generate one word at a time. So we want to prepare the training data accordingly, where the next word in a sequence represent the largest or represent the target to predict. For example, sample text is LLM learn. These are not predicted words. Next will be LLM learn to. Next will be LLM learn to predict. This also we can call this as a sliding window, that we are taking one element at a time but keeping a context window size that I know any of these number of tokens at any point in time. So the LLM can't access word past the target, and target to predict, these are targeted words, to be predicted word, tentatively to be predicted word, and this is our input the LLM receives. So LLM receives these inputs, initial input, and these are expected target words to be predicted by the model. Let's implement the same on our existing content, which is Wizard of Oz text file. Let me read this file, and if I use this tokenizer, the tick token, then it will use the 60,960 tokens are there in that file, where for each text chunk we want the input and the target, since we want the model to predict next word. Now understand the terminology, understand the training, how the training should happen, because we have to train the model like I give you 2 words, next word is this. Now I'm giving you 3 words, next word will be this. So keep maintaining the context. You will be in a position to predict the next word if I train you on the same content multiple times. Since we want the model to predict next word, the target are input shifted by one position to the word at a time. So which means I'm printing that for the purpose of representation. These are our token IDs. So first token ID is 440, 57, 11 and 412. Next word will be whatever the next word is. So I'll take 57 from here, 11, 42, 412 and 4825. Next will be 11, 42, 412, 4825 and the next token. This is what we will be using to train our model. One by one, the prediction would look like this. You printing this in the form of actual text. Like first 440, 57, then 57, 11. So I'm talking about one element at a time. 57, 11, 412. 57, 11, 442, 4852 and so forth. Then after this, if I want to use the same numbers in the form, that was token IDs, these were token IDs. If I want to convert these into token IDs into words, I'm using decode function. So first word was O, then expected next token is Z, then next token is OZ, next token is comma, then OZ comma, the next token is E, OZ comma E, next token is TC. This is how we are going one step at a time, sliding or shifting with sliding window concept. And this is how we train the model. We'll take care of the next word prediction in a later session also, after we cover the attention mechanism. But for now, implement a simple data loader that iterates over the input data set and return the input and target shifted by 1. And this is what our word is. Example understanding. Let's look at this example a little closely. This is our sample text in the first window, in the heart of. So I'm using these 4 tokens. The next predicted token will be the heart of the. Then next will be heart of the city. Next will be of the city stood. So we are using this sliding window and we are presenting them in this tensor containing the input, that is matrix containing the input. So first was input in the heart of. Next is the city stood the. So this is our input containing the inputs, and this is the implementation of this. Now we are defining the functions, and now let's see how it look like. These are our tensors, I mean the data token IDs and the next tokens. So the first and the target predicted tokens or the next series of tokens. So an example using stride equal to the context length, here we are using 4. 4 is not a very good number to understand. By the way, the GPT-2 model have context window of 2048, not 4. Please understand. And these have much bigger context window. So input batch of 1 is in the heart of, and input batch 2 is the city stood the, right? So we can also create batched output. Note that we increase the stride here so that we don't have overlap between the batches, since we overlap could lead to increase in overfitting the model. And this is the example of our tensors. We are printing only the token IDs. So this is our input tensor and this is our output tensor. Creating token embeddings now. The data is already almost ready for the LLM to consume.
One question: the IDs don't have any. I mean, they're serial numbers. They don't need. You don't need them between 0 and 1 or minus something and plus something. IDs can be 0 to infinity.
Too early to talk about, because right now we are talking about the vocabulary. Each token has a number, and we are talking in terms of token IDs.
Yeah, but we will stop working with tokens from here on, and we work only on token IDs now.
Yes,
right?
token IDs, but then into the final word. This is the final part. Token IDs will not be good. We will not be using token IDs. We'll be using, this is the basic concept. This is now the concept which is ready for to be implemented as a tokenizer or embeddings.
Okay.
The data is almost ready for the large language model, but lastly, let's embed the tokens in a continuous vector representation. This is what is missing because so far we have the words and we have the token IDs of each of the token. We need to implement a continuous vector representation of the same using an embedding layer. Usually these embedding layers are part of large language model itself and are updated or trained during the model training. So here we are so far: input text, tokenized text and token IDs. We want to understand this part now. That is converting these token IDs into vector representation, that is token embeddings. Suppose we have the following 4 input example with token IDs 2, 3, 5 and 1. After tokenization, we are talking about token IDs. So we call it as input IDs, torch, tensor 2, 3, 5 and 1. We are taking these 4 token IDs only, 4 elements only, for the purpose of illustration. So these are our token IDs or input IDs to be precise. For the sake of simplicity, suppose we have a small vocabulary of only 6 words. Vocabulary size around 50,000 words are there. And we want to create embeddings of size 3. We are not talking about embeddings of 1024 dimensions. Again, this is for illustration. We are creating embedding of size 3 only. So these are the token IDs. These are total vocabulary of 6 words, and embedding size is 3. Dimensionality of our vectors will be 3. So we specify here vocabulary size 6. Output dimension is 3. Because dimensionality is 3, we are defining here. So manual seed will be 123. You give any number to it. You give any seeding number, some seeding you give. So embedding layer I can implement using this vocabulary size of 6 words and embedding to be created of size 3 dimensions. So this is how I'll define it: torch, NN embeddings, vocabulary size and output dimensionality. This will create my embedding layer. This would result into 6 by 3 weight matrix, and this is how the matrix will look like. So we created embedding layer using the class from torch, using embedding function, embedding method of that. So this vector representation, this floating point representation, this 3-dimensional vector is actually the embedding of the corresponding token which corresponds to the ID number 3 in our vocabulary. Let's assume the word is dog. So these are embeddings for the word dog. So printing these input IDs, and this makes my proper embedding for the given content. And this is what we are referring: weight matrix for the embedding layer. This is how the weight matrix will appear as. Token IDs to be embedded, and embedding token IDs corresponding to this weight will be converted to this like. BytePair encoding has a vocabulary size of 50,257 total vocabulary, not 6 words. Suppose we want to encode the input into 256 dimensional, not 1024, not 384, the minimum size to understand 256.4 representation, then this is going to be our representation. Vocabulary size 50,257, output dimension 256. If we sample data from the data loader, we embed the token in each batch into 256 dimensional vector. If we have a batch size of 8 and 4 token each, batch size means how many data will be processing, 4 token in each. This results into 8 by 4 by 256 tensor. And this is how we can print that now. Token IDs and input samples. This is the size 8 by 4. Now this is our token embedding layer inputs, and GPT-2 uses absolute position embedding. So we just create another embedding layer for the understanding purpose, and we are printing them as well. The size is 4 by 256, 8 by 4 and 4 by 256. To create input embedding used in LLM, we simply add the token and positional encoding. So input embedding is token embeddings plus position embeddings, and this will be the our shape. So torch size will be 8 by 4 by 256. In the initial phase of the input processing workflow, the input text is segmented into separate tokens. Following this segment, these tokens are transformed into token IDs based on the predefined vocabulary. So this is what we have just now created, the token embeddings, which will be consumed by our transformer architecture. Building large language model from scratch, BytePair encoding BPE. Let's run through this also. What I demonstrated through the program will understand that here also. We'll repeat. It is a revision that will make the concept a little more clear. GPT-2 uses BytePair encoding as its tokenizer. This allows the model to break down words that are not in its vocabulary into smaller subword units or even individual characters, so that it can handle out of vocabulary words also. For example, GPT-2 vocabulary doesn't have the word unfamiliar word. It might tokenize it at unfam plus illier plus word. It might do that. The original BPE tokenizer can be found.
Is there a word called unfamiliar word?
I'm assuming, sir.
Achha,
I'm
as
using
if it's
if.
a typo.
No,
Okay.
I'm talking about, no, I've deliberately done that.
Okay.
Understand the context, sir. Understand the idea.
Okay. You're assuming that is a legitimate English word, unfamiliar word.
Yeah, any assumption, you can take any word.
Okay, got it.
We will use BPE Tokenizer from our from open source tick token library, which implements core configuration, core algorithm in Rust to improve the computational performance. The BPE Tokenizer break down unknown words into subwords and individual characters. And this is the tokenizer, importing it. Data sampling with a sliding window. We train LLM to generate one word at a time. So we want to prepare the training data accordingly, where the next word in the sequence represent the target to predict. Like this one, what I explained in the lab. Given the text sample, the extract input blocks as subsample that serve as input to the LLM, and the LLM's prediction task during training is to predict the next word that follows the input block. During training, we mask out all words that are past the target, meaning when we are talking about word 1, we mask other words. That is called masking. We can't go third word from now because we are at this token right now. This is masking. Note that the next text shown in here would undergo tokenization before the LLM can process it. However, this figure omits the tokenization step for clarity, because we are not using word by word. Actual thing is happening in the form of tokens only, or token IDs to be precise. For each text chunk, we want the input and the target. Since we want the model to predict the next word, the targets are the input shifted by one position to the right, and this is positioning and shifting the token IDs towards the right, one token at a time. One by one, the prediction would look like this one, the same thing as you have seen in the screenshot and during the lab demo. Implementing the simple data loader. We will take care of the next word prediction in later session, but as of now, for now, we implement a simple data loader that iterates over the input data set and return the inputs and the target shifted by 1. We use a sliding window approach, changing the position by +1. Create dataset and the data loader that extract chunks from the input text dataset. This is the same class now, implementing the same, and this is the code part of it, same example. Let's test the data loader with a batch size of 1 for an LLM with context size of 4. Once again, I'll repeat, batch size, normally we define that okay, we'll batch 48 tokens or 60 tokens or 100 tokens. There's a batch size, fixed size. And the context size is how many tokens model can process at any point to generate the next token. That's important point to understand. And this is what we are talking about. The simple example we are considering, not bigger size, for clarity, for understanding purpose, size 4. An example using stride equal to the context length here is 4. And this is what I have explained during the slide, during this demonstration also. Avoid overfitting. We can also create batched output. Note that we increase the stride here so that we don't have overlap between the batches, since more overlap could lead to increased overfitting in this example. So create data loader version 1, row text, batch size 8, maximum length 4, stride 4, shuffle false, and this will create this data iteration, that is data loader. We created input, target, and next data. So we are printing input and then targets, what we have seen here. Creating token embedding. The data is already almost ready for the LLM to consume now. Let's embed the tokens into continuous vector representation using an embedding layer. Usually these embedding layers are part of the LLM itself and are updated or trained during the training of the model. And this is implementation: input text, tokenized text, then token IDs, and then token embeddings, which we are at this step now. We are going to create the token embeddings, and a decoder only, that is transformer like GPT, and the final post processing and the output layer. Suppose we have the following 4 input examples with input IDs 2, 3, and 5 and 1 after tokenization. And then for the sake of simplicity, suppose we have a small vocabulary of only 6 words and we want to create embedding of size 3. So we define vocabulary size and output dimensions, and we use a manual seed. Embedding layer is created using vocabulary size and output dimensionality. This would result into 6 by 3 weight matrix, and this is what we can print: embedding layer dot weight. Based on this embedding layer dot weight means we call this dimensionality or weight matrix of the same embedding layer, where we define the vocabulary size to be this 6 and output dimensions to be 3. And this is the weight matrix of same dimensionality, and we call this using weight method of this object embedding layer, which we created here. The embedding layer we used is a more efficient way of implementing one hot encoding followed by matrix multiplication in a fully connected layer. Because the embedding layer is just a more efficient implementation that is equivalent to one hot encoding and matrix multiplication approach, it can be seen as a neural network layer that can be optimized via back propagation. We are using a few terms which may not be fully understandable right now, but as we progress, we will have more clarity on the same. To convert a token with a token ID 3 into a 3-dimensional vector, we can use this embedding layer torch tensor 3. So this token is converted into this token in the vector representation. The above is the 4th row in the embedding layer matrix. This one, 4th row, this one here, example converted to this one. The embedding of all 4 ID values above, we do this. So the embedding layer is essentially a lookup operation. Like when we are looking for this, these are token embedding token IDs. We were looking for these. So where the token ID is present. Embedding layer convert IDs into identical vector representation regardless of where they are located in the input sequence. Positional encoding, this is what you asked, are combined with the token embedding vector to form the input embeddings for a large language model. So it's a combination of positional embedding, they are combined with the token embeddings vector to form the input embeddings for the large language model, and this is what we do. So these are input embeddings, the vector representation, these are positional embeddings and the token embeddings. The BytePair encoding has a vocabulary size of 50,257. This is the size. Suppose we want to encode an input token into 256 dimensional vector representation. This will be the ideal size. Max length 4. Downloader, we download this batch size 8. Max length, maximum length of this defined with this size, and stride max length, and shuffle false. So if we sample data from the data loader, we embed the tokens in each batch into a 256 dimensional vector. If we have a batch size of 8 with 4 token each, this will result into 8 by 4 by 256 tensor, and this is what I demonstrated in the lab as well. GPT-2 uses absolute position embeddings. So we just create another embedding layer. To create input embeddings used in a large language model, we simply add tokens and positional adding together. That is token embeddings plus position encodings. Position encodings is implemented as position encoding layer, the torch arrange max length. That will give the position. This is, we can print the shape also. This is 4 by 256, and this is our token embedding. So token embeddings and position encodings, if we add the two, that comes out to be your input embeddings, which is token embedding plus position embeddings, and we are printing the shape, what is the size of this. So in summary, the initial phase of the input processing workflow, the input text is segmented into separate tokens. Then these tokens are transformed into token IDs based on the predefined vocabulary. Finally, the implemented token embeddings, and this was the flow we have tried to understand in this session, in this lab also, using BytePair encoding. This is what the overall flow of the session was. That's all for this session. Thank you very much, team.